So, welcome to the lecture on 2 degree of freedom systems. In this lecture, we will discuss the combined rectilinear and uh, angular motions. So, we have several examples of the combined motions. In the previous lectures, we assumed that we took the cases when the both masses had the motion in translational direction. So, but there are some mechanical components, mechanical systems when there are two motions, one is in linear and other is in angular. So, here we can see one example of the car, and let's this there is the car and you can see the stiffness element K1 and K2, and there is center of gravity of the car. So, now when on the road surface the car can go downward, so it is a linear motion, so center of mass can go downward, as well as that if there is some unequal compression in the spring, so one can be more compressed than other, so there could be some also some angular motion of this car. So, let us discuss this motion. So, we have this. So, this is its center of mass and these are the springs . And this is L1, this distance is L1 and this distance is L2, and this is M and J. J is the moment of inertia of this mass about its axis passing through the center of mass, and J is equal to J equal to m r square, where r is the radius of gyration. So, it is radius of gyration. Okay. So, this J is the moment of inertia about the center of mass. This is L1, L2, and these springs has the stiffness K1, K2. Now, this has 2 degree of freedom, one is this direction x and other is the rotation theta. Okay, so there are 2 degrees of freedom, one is the linear or translational, other is angular or rotational. So, here we now take the case when the both degrees of freedom are disturbed, then only we can have the case of free vibration, and by studying this case we can find what is the natural frequencies of vibration. So, we have now this line and we have now the situation like this. So, here it is displaced with x and here it is theta, this is theta, and these are the two springs, they are compressed or here. Okay, this is K1, K2. So now we have to write the equations of motion. So we have to make a free body diagram that we have made here, and for each degree of freedom we have to write one equation. So here we have in linear or direction, so we have m x double dot equal to, okay, so what are the forces here on the spring? So we have the forces here on the mass. So this is the mass, so here are the spring forces, and this is x double dot in this direction. So these spring forces, what are these spring forces? So because what is the, these forces are k1 times the compression of the spring. So about the first spring, so first it is compressed by x, and then here due to rotation it is extended here. Back, so k1 into x minus L1, so this is L1, this distance is L1, so this is L1 times the theta, because this angle is theta, so L1 theta is this distance, so x minus L1 theta. So this is the force that will be applied from this spring. Now what about this other spring? So this spring, so again K2 into the compression. So here it is compressed by x, so this is the, so I have to redraw this, so this is so that it is more clear and we can understand this. So here, so this is the initial axis, this was the initial axis, okay. So this was the axis just because of translation, so this is the translational axis, and then this is the rotational axis, and that is why here it is x minus L1 theta, and this is x plus L2 theta, because this distance is L2, this is L2, so this is x plus L2 theta. So mx double dot equal to, these forces are opposite, so it is minus k1 x minus L1 theta and then minus k2 x plus L2 theta. We can simplify and we write mx double dot, so this is k1x and here is k2x, so we can take other side, so it is plus k1 plus k2 x, and theta term if we keep here, so it is k1 L1 and this is minus k2 L2 and here is theta. Now what about the rotational degree of freedom? So for the rotational degree of freedom we will have j theta double dot, because here theta is the degree of freedom and j is the moment of inertia, that is equal to the moment about that point, the center of mass. So these are the forces and moment, we have to take moment. So if we see, if this is the degree of freedom theta or theta double dot, so this force is giving the, so this direction is clockwise and this is giving clockwise, so it will be plus. So k1 x minus L1 theta. So this is the force and the distance is L1, so the moment is this force into L1, so into L1, but this is giving anti-clockwise, so it is minus k2 x plus L2 theta into L2. Now simplify this, so j theta double dot, so we bring the theta terms here and x terms other side. So this is k1 L1 square, this side plus, and this is k2 L2 square, so this is plus k2 L2 square theta, and equal to, this is k1 L1 x minus k2 L2 x. So this is equation number 1, this is equation number 2. Now we can see one thing, that so this is the equation of motion of the linear degree of freedom, but here we can notice that there is also the degree of freedom term theta in this equation, and similarly this is the equation of motion of the rotational direction, angular direction, but here is the degree of freedom term x, here the linear term, means the motion of linear motion is influenced by the angular motion and angular motion is influenced by the linear motion. So this kind of situation we call as coupling, so we call it coupling of modes, okay, because these motions are coupled, and how they are coupled? They are coupled with these terms. We can see these terms are the same, they are equal and they are coupled here. Now we can simplify these equations. So let us assume that A equal to k1 plus k2 by m, and here j is already we assumed m into r square. So k equal to A equal to k1 plus k2 by m and B equal to k1 L1 minus k2 L2 by m, and C equal to k1 L1 square plus k2 L2 square by j. So now we can rewrite this equation 1 and 2. So equation 1 will be x double dot plus ax, because we are writing here ax equal to b theta. So this we call equation number 3, Then equation 2 will be, so here theta double dot plus c theta equal to b x. Here it will be by j and j equal to m r square. So, r square will be here and this is equation 4. Now, from the equation 3 and 4 what we can see that the equation is coupled because of the b. If we put b equal to 0, what will be the equations? They will be x double dot plus a x equal to 0 and theta double dot plus c theta equal to 0. So, the both equations are uncoupled because in the equation of motion of x there is no theta, in the equation of motion of theta there is no x. So, these equations are uncoupled and they are uncoupled because the b is there to decide their coupling. So, that is why b is called the coupling coefficient. So, here b is we call as coupling coefficient, and so b equal to 0 means what is b? B is the here. So, K1 L1 equal to K2 L2. So, this is condition in this case for not permitting the coupling of the two degree of freedom system. So, when they are uncoupled we can find from here what is their natural frequency. So, omega n1 that is the natural frequency in the linear direction, that is under root a, and this is equal to k1 plus k2 by m. Omega n2 the second natural frequency of uncoupled system is under root c, and that is equal to under root k1 L1 square plus k2 L2 square by j. Now, when these systems are coupled we have to solve this. So, again we will assume that the system is vibrating with the same frequency omega in the free vibration, and so we assume that x equal to x sin omega t and theta equal to beta sin omega t. So, where x is the amplitude of the linear oscillation and beta is the amplitude of the angular oscillations. So, now we put these values in equations 3 and 4. So, we will from here x double dot equal to minus omega square x sin omega t, and here theta double dot equal to minus omega square beta sin omega t. So, we put these values. So, here minus omega square x, so we can write like minus omega square plus a x equal to b into beta, and from here we get x by beta. So, x by beta equal to b upon a minus omega square. Now, the second equation we will get, so it is theta double dot So it is minus omega square beta plus c theta is, so it is beta. Of course, the sin omega t terms both sides will be cancelled, or that is the that case we are not taking. So c beta here equal to b by r square into x. So from here we will get that x by beta equal to c minus omega square upon b by r square. So we are getting the ratio of the amplitudes of the two motions, 2 degree of different degree of freedom motions, and they should be same. So we equate them. So b by a minus omega square equal to c minus omega square b by r square. So we solve it. So it is b square by r square c minus omega square and a minus omega square. So this is c into a minus c omega square, c into a minus c omega square minus a omega square plus omega power 4. So from here we can find omega power 4 minus a plus c omega square minus a plus c omega square plus ac plus ac minus b square by r square, that is equal to 0. So now this equation is quadratic in omega square. So this equation is a quadratic equation in omega square, and of course this equation is the frequency equation as we discussed. So it is frequency equation. So it means that when we solve this frequency equation, we will get the natural frequencies of this system. So we will get two natural frequencies that are real, and so we will solve it. So omega square equal to, so minus b, so it is a plus c plus minus b square minus 4 into 1, because it is a is 1 into c. So it is ac minus b square by r square by 2a. So 2a is a is 1, so it is 2. So now we have a plus c by 2 plus minus 1 by 2 under root. So a plus c square, so we can a square plus c square plus 2ac minus 4ac and plus 4b square by r square. So, we will have a plus c by 2 plus minus 1 by 2 under root a square plus c square minus 2ac plus 4b square by r square. So, we will have a plus c by 2 plus minus 1 by 2 under root. So, it is a minus c whole square plus 4b square by r square. So, omega n1 will be the lower natural frequency, and the lower natural frequency when we take minus sign. So, omega n1 will be under root a plus c by 2 minus 1 by 2 under root a minus c whole square plus 4 b square by r square, and omega n2. So, omega n2 will be when we take plus sign. So, a plus c by 2 plus 1 by 2 under root a minus c whole square plus 4b square by r square. Okay, so we get omega n1 and omega n2. Of course, when we put b equal to 0, if we put b equal to 0, so the system is uncoupled. When b is 0, the system is uncoupled, and so we will get here under root a plus, so omega n1 is under root a plus c by 2 minus a minus c by 2, and that is nothing but under root, so a by 2 minus a by 2, so it is c under root c. So, this natural frequency of this degree of freedom, and omega n2 equal to, so it is plus, so it is under root a. So, that is the natural frequency of this system. Okay. And when we have find this natural frequency, now if we put this natural frequency in this x by beta expression, so x by beta for first natural frequency is the first mode shape. So, we can put b upon a minus omega 1 square. So, that is the first mode shape, and if we put x by beta 2, so the second mode shape, that is b by a minus omega 2 square. So, this is the second mode shape, and so we can find these mode shape. Okay, so we see that how the linear and angular motions that can be coupled, and because that the one motion can be part of the other motion, okay, and that will govern the dynamics, vibration dynamics of that motion. And there are some coupling coefficients, and if they are 0, the system is uncoupled, and then the system, when we have these coupled equations, we can solve it, and we can find the natural frequencies and the mode shape of the system. Okay, so I stop here, and thank you for your attention, and see you in the next lecture.